Um, Good morning, good afternoon, or good evening perspective to where are you? Thank you for joining us for this webinar organized by the Canadian Geotechnical Society Young Professional Committee. My name is Rajit Dayaratna. I am a geotechnical engineer from St. John's, Newfoundland, and I am serving the CGS YP committee as the knowledge lead and will moderate today's webinar along with Alex. CGS YP committee initiated this webinar series to allow young professionals to enhance their knowledge in a range of areas of geotechnical engineering. We successfully conducted 2 webinars in January and February. If you are interested in listening to our past talks, recordings are available on our YouTube channel. I will post the link in the chat shortly. Before we get started, there are a few housekeeping notes. To avoid any disturbance, we disable audio and video access. If you have any questions, please use the chat option. The presentation will take about 40 to 45 minutes, and there will be a brief Q&A session at the end. If you have any questions for the speaker, please type them in the chat, and I will take them as they appear. Today we have a well-experienced geotechnical engineer with us, Mr. Iain Gidley from Turbo Engineering. Mr. Gidley obtained his master's in geotechnical engineering from the University of Calgary in 2009. Since graduation, he has been working with Turbo Engineering in their Calgary office. He has worked on a wide variety of projects, including foundation, bridges, major infrastructure, deep excavation, tunneling, soil structure interaction, pipeline, dams, tailings, numerical modeling, and laboratory testing. He specializes in understanding soil behavior, and colleagues have remarked that he has as many words for modulus as the Inuit have for snow. So without further ado, I would like to invite Iain to start his talk on understanding laboratory and in-situ testing within geotechnical assessment and design. Over to you, Iain.
Perfect. Thank you, Rajit, for the introduction. Sharing now. So I'll get going. As Rajit said, talking today about lab and in-situ testing, and we're trying to put it in context of the framework that we work within. And the focus today is on lab and in-situ testing. However, the aspects of the larger investigation and design process, and to properly undertake a lab or an in-situ program, we need to understand where we're fitting into that larger process. Specifying lab tests is one thing. It's easy to say, I want a triaxial, I want a direct shear, I want DSS, but we need to figure out what to do with them and figure out when to use those. And to do so, we need feedback from other aspects of the design process to really figure out what we should be doing. And since this is kind of like this 101 concept, I think in school we're given problems, which we get a problem, we're given the tools to solve these problems. In practice, we need to generate the context around that problem so that we can figure out what tools we need to apply to solve it. I think that's the big jump, and that's what the focus of the talk today will be on. So I had, thought about this I had this pyramid idea of how we have these building blocks of geology and things like that, and then I remembered this lecture by Dr. Berlin, and it turns out he'd already made a very nice figure, so I could just steal from him. So I think, like all of us, we try and take from those who know. So this is what he had referred to as the geotechnical triangle. And the geotechnical triangle, it relates 3 key aspects that we see in all projects in geotechnical engineering, from the very simple to large and complex. And we're talking about the ground profile. So that's kind of the geology and our understanding of the ground. The behavior, so this is the behavior that we measure in the field. It's also the response the ground has to whatever we are doing to it, being an excavation, building an embankment, so on and so forth. And then the model. So this is how we relate the ground and the behavior together. So this might be a numerical model, it could be a simple hand calculation, depending on the size of the project. And then these are all tied together by this empiricism, case histories, and experience. And the way that I like to think about it is growth is pain, but you get to choose whose pain you grow with. So you can either grow through the pain of your own experience, where the natural learning process, we make mistakes, we get a result that is unfavorable, and we learn from that. The other choice is other people make mistakes, and we can learn from understanding their mistakes. And that's this empiricism case history. So we understand what's worked, what hasn't worked, and we can tie everything together. So today, we're really going to focus on these kind of pieces. So this ground exploration a little bit, so the in-situ testing and measurement lab field testing observation. So we're going to kind of tie these into the triangle at large. So when we try and put testing in context, it doesn't occur in a silo. It's integrated into this concept of the project. At the start of the project, we tend to know very little about the site, and we build our knowledge through understanding what we're going to build, how we're going to build it, the local geology from maps, air photos, the results of our field investigation, lab testing, what our calculations or numerical models are telling us, and our experience with similar designs or materials. So as we are going through this process, we're acquiring new insights, and we have to continually ask ourselves, does this knowledge that I'm gaining match what I have learned and my expectations based on what I have learned to date? So there's this constant cycle of, okay, I've added something new. Does this fit inside this model that I am building? And I think this starts with geology. I'm unfortunately, or fortunately, I'm a geotechnical engineer. My geology in school was relatively limited. Through work, through practice, I've had to gain an appreciation for geology. And it really is the first step in understanding what conditions may exist at a site. And we have published maps that are typically available that tell us what we might expect at surface, what we might expect from bedrock. And these are really useful in planning the investigation layout, equipment selection, understanding what types of soils to expect, planning the lab program, and understanding the potential behavior of the soil. These maps are typically available at a large scale. And if you work with someone who's a geologist or geomorphologist or terrain specialist, they can improve upon that interpretation. So from that desk study, we have a reasonable idea of what soils are present. And we probably have a good idea of how each unit might behave for a given application. So, I ask kind of tongue in cheek, if we can figure all this out from maps and air photos, why do we do an investigation? So mapping itself is imprecise. Air photo interpretations and art, it tells us what to expect, not what's actually there. You can't see beneath the surface. The properties of materials and groundwater conditions will vary from site to site. So it's the same. I have some test holes from another site. It says it's in similar geology. Does that apply to my site? I don't know. But you're starting to build what your expectations are for the site. So then we're going to go and we're going to do a field investigation. So we've got this idea of what we think is there. We've taken that idea and now we're going to plan our investigation. And we're going to plan it depending on the complexity of what we're trying to do and the complexity of the geology. So the purpose here is to build a ground model based on targeted information at specific locations. And it's really important that we get an accurate description of the materials that we're observing while drilling. And typically we only bring back small subsamples to the lab. So that site engineer, whoever's out there, they're the one who's really seeing the complete picture. And if you can, high quality photos are valuable. And in situ testing is also valuable because hopefully we can test large portions of the soil with minimal disturbance, and we can get some idea of how the ground is going to behave. I think it's important when, like, our first job is typically being out in the field. You want to have some idea, why are you there? What are you looking for? What matters? So it's important that we investigate with purpose. Why are we doing this? Why am I here? What is my purpose in life? What is my purpose being out in the field? So what am I doing this for? Is it for a shallow foundation, a pipeline, a directional drill, piling, embankments, slopes? What am I looking for? Am I looking, if I have a directional drill, maybe I'm concerned about gravel layers at depth. Or for an embankment, I'm concerned about high plastic clays, interbedded materials, weak materials. So you've written a proposal that says, I'm going to take this many Shelby tubes, or I'm going to take these many samples. But in the field, you should have this context of, okay, what matters? And then you can adjust that program so that you're actually collecting the right things. So, you know, and we also need to be thinking about how we're going to do the analysis. So what properties might I need for if I'm doing deformation or strength or looking at consolidation? Different constitutive models require different tests. And we really need to consider all these factors when we're planning the investigation. And we may select different lab tests and in situ tests. And I think one of the things, you know, I always try and say is, you know, we come up with a proposal, we plan how much lab testing we're going to do, and say we've got a $15,000 budget for lab testing. Like, and we say, okay, this is based on X number of moistures and traxials or whatever testing we're going to do. But that's really the budget. Like when we get the samples back and we see what we've done from testing, I'm a proponent that we should consider saying, okay, here's what we've collected, here's what we've seen, here's what we planned. Should we adjust our plan? And, you know, in situ testing, lab testing, there's a lot of different things that we can do. We can start pretty simple with in situ standard penetration test, Becker hammer, large penetration, dynamic penetration test, vein shear, cone penetration, seismic, pressure meter, self-board, pre-board. There's tons of different methods. Lab testing, very simple, water content, limits, grain size, strength testing, direct shear, direct simple shear, traxial, UCS, consolidation, permeability, saltwater characteristic curves. There's so many different tests. And there are resources to help you plan which tests to use. I think, again, it comes back to this context. So, and we'll work through this with an example here in a bit. So when we think of in situ testing, the benefits are we're testing the in situ condition, you know, at the in situ stress level. We can use this when sampling is difficult, granular soils, or when we think significant disturbance would occur, and there's sands below the water table. It's nice, depending if we're using cone, we can get a continuous profile. Some of these methods test a large volume of the ground, much larger than we can test in just from samples brought back to the lab. And we can do this faster than standard drilling methods. On the limitation side, a lot of the tests don't recover any soil samples. So we have no idea what material we just tested. We're hoping that the borehole we drill adjacent to it will tell us what was there. Maybe, maybe not. The drainage conditions and the location of the water table can complicate the interpretation and understanding the results. Many of these methods rely on empirical correlations to assess material parameters. Maybe, maybe not applicable. Disturbance on drilling can impact the results. And then the test could just be done in a different direction than what's important to you. So maybe the test is done horizontally, but you're really concerned with vertical parameters, or vice versa. So I put together this fictional, not fictional, site example that to try and illustrate this point. So let's say we've got a client they want to build a footing to support a mainline block valve for pipeline concerns or settlement and bearing capacity. So we're going to build a kind of a spread footing at ground surface. That's what they're thinking about. So we do a simple investigation, limited scope and budget. The investigation consists of a single test hole, altering grab and SPTs every 5 feet. Basic lab program, water content, limits grain size. From the geologic mapping, superficial glacial clustering unit, which I'll call a GLU, and we have bedrock 15+ meters. Based on the project, the materials present, some initial concerns. Okay, so I'm going to put heavily loaded valve. I'm concerned maybe the strength of that GLU or the pre-consolidation pressure of the GLU. It might be normally consolidated or lightly over consolidated. Maybe I'm concerned where bottom is if I have to do settlement calculations. So these are kind of these thoughts I have trying to relate that triangle, my first pass through the triangle in planning the investigation. So we go do the investigation, have our field logs here. So we've got a clay, medium and high plastic, berm, interbedded with sand silt layers. And then the driller says there's a layer. We've got clay, medium plastic, very stiff, trace gravel, soft layer at 12 meters, refusal 21. And then here, this is our initial, so we brought the samples into the lab and they've run some initial water contents. So we start getting our testing back. We ask ourselves, what do we see? So from the geology, I had an expectation. Superficial GLU. Okay, is this my glacial clustering unit? Is this till? Maybe I have glacial clustering over till. Wasn't in my mapping, but I see a shift in water content, shift in the description, shift in the stiffness. So I'm starting to try and put these things together. And then this refusal. So they're auguring what happened. Did I hit bedrock? It's about the depth I expected, a little deeper. Is it rafted? It's till. There's boulders. Do they refuse on a boulder? And I've got this outlier. Is that a high plastic layer? So again, we start layering on more data. We start to look at things with more pieces here. So now we're add in our limits, add in our SPTs. So does that confirm or does it challenge what we saw? So now we're looking at this upper unit. Got a relatively high liquidity index, so that's where the moisture is relative to the plastic limit and the liquid limit. So that suggests this material might be lightly over consolidated. I expect it to be a little more compressible, potentially lower strength. I see that in the SPTs, low blow counts. So I'm thinking a relatively low undrained strength. This layer certainly got higher blow counts. So it's probably stiff, pretty strong. Liquidity index here is pretty low. So I'm thinking it's relatively stiff. Probably not going to see a lot of settlement there. And then this guy here, so still relatively low liquidity index. Is it maybe a weak layer? I certainly got high plasticity. So it's high compressibility, but maybe high pre-consolidation pressure. This is where the geology, you're going to ask yourself, if this was a slope, you might be asking, well, have I seen landslides nearby? Are they sliding at this layer? Is this layer continuous? So you may start thinking about different questions. It depends on what your application is again. So this is why everything has to be thought of in context. So let's follow through on just what these lab tests can indicate. So these are just the basic. These are the ones that we run pretty much all the time. From the water content and the limits, we can get pretty significant insight into the behavior of the materials. Liquidity index is useful in understanding the stress history of material. My rule of thumb, high liquidity index tends to be normally to lightly over-consolidated and to expect more settlement, potentially lower strength. Low liquidity index, so kind of less than 0.2, tends to be glaciated, over-consolidated. We expect less settlement. So materials subjected to the same stress history tend to go to the same liquidity index. So the water content itself can be useful in identifying high plastic zones. So for example, in the oil sands, we get cores of this material. It's a clay shale, and it's basically just gray. It's just never-ending gray, and then you've got these intermittent layers, like indicator layers that we'll measure off of sands. So they kind of tell us, okay, here's this layer, and then it tells us what facies are present. But another way that we can find where these weak layers are is we go through and look at water contents on tightly spaced intervals, and you can actually find these zones that are very high plastic where we expect to see movement. And I think, for example, there's a dike there. It was originally designed 4-to-1 side slopes, and due to movement on these high plastic layers, I think it's 25-to-1 side slopes. So it's that was one of these things that they found through pain. So they had built this original design, and then it started moving, and they had to keep buttressing this to support and stabilize the structure. But now through their pain, we've got this, okay, we have to be cognizant of this high plastic layer. So like anything simple, it's not foolproof. It's really just a first screening test, and it might be sufficient for relatively simple sites or small jobs. There's a sampling bias, drilling influences, disturbance can affect the results. And we need to be really careful in layered materials, especially glacial lacustrine. The testing, you have to think about how's the testing done. We take the sample, they need a certain amount to do the test. So if you've got thinly interbedded materials, they're mixing up the clay, the silt, and the sand layers, which means the limits you're getting back, it's a blended behavior. So the limit might be medium plastic, but reality is you have a high plastic clay with non-plastic interbeds, which can lead to overestimation of strength, permeability, and performance. So just the SBTs here again, like talking through them, like we've got low blow counts in the upper bit. It's confirming the assumption that the material is soft and compressible. And then lower down, it's confirming the assumption is relatively strong and stiff. So we've made our assumptions, and then as we add more and more layers, they're either confirming or they're challenging those. And I think I'd just take a pause to talk about the SBT. This is something that you will probably come across the most. It's a very simple test where we take a pipe and we smash it into the ground, a set distance with the same energy, and we've used it forever. The benefit, it returns the sample and has that long history subject to disturbance, especially in coarse grain soils below the water table. Soils can loosen through the drilling process, just hard drilling, high advance rates, unbalanced water heads. Rocks or bedrock fragments can distort the tube, causing high values. Something we should do that we probably don't do often enough is getting the hammer energy so that we can do at least simple corrections. And then when you are using correlations, you need to be cognizant of what energy, what N you're actually using in that correlation. Is it N, which is an uncorrected blow count? Is it N60, N060, which means the blow counts are corrected for energy? Is it N160, blow counts normalized for atmospheric and corrected for energy? So all of these correlations will be slightly different. And if you use the wrong N, you can be conservative, you can be unconservative. I had a project where we got these SPT values back and they were very low. And then we looked at the camera energy and the thing was like 90% efficient. And the standard N60 60% efficient. So you had basically 50%, like you were underestimating things by 50%. So it's something to be cognizant of. So let's continue on our fictional site here. We need to get some properties to do our assessment, settlement, bearing capacity. And this is what I'm talking about before. Like we've got this ground exploration. So we've gone and we've got tests. We've done some lab and field testing, and we're going to do some modeling. And we're going to try and tie these together through this empiricism, through case histories, through the experience of others. So say for settlement, we need the pre-consolidation pressure. I prefer to use over-consolidation margin. You can talk about that after if you want. There's the compression index, CC, CR, strength, undrained strength, frictional strength. And we'll go through a process of saying, okay, I'm going to use some correlations to come up with these properties. I'm going to fit these to come up with design lines. So I've shown just kind of some in red, what you might choose. I don't really want to talk through the correlations, which correlations I've used themselves, but we're going to go through this process. And I think what's important is understanding what you're doing when you're using a correlation. So we've done this in-situ testing. We're trying to get parameters to do the analysis. We're going to use these correlations that provide this link to our collective engineering experience. Why should we use anything else? There's lots of assumptions that go into the development of the correlations. And it's the same, there's lots of assumptions that go to picking a number out of a book. You go to Bowles or Holson Kovacs or whatever, and you're just saying, I'm going to take this number out of this book, and I'm going to use that. There's assumptions that go into that. And you have to ask yourself if they're representative of your actual site conditions. Does a clay from the UK or Illinois behave the same as a clay from Alberta or Quebec? Probably not. But the better question is, will they behave similarly? Generally, they provide a conservative estimate of design parameters. For a small project, it may not matter, make very little difference to the cost of the final design. So you could go and do a bunch of expensive testing and you have enough uncertainty, it probably doesn't help you. For a large project, that conservatism could be expensive. And we have to be careful. Like not all correlations are conservative. There are several published, well-used correlations that give unconservative parameters in certain areas. So in Alberta, there's correlations that are widely used, and I've seen used in the US, in Eastern Canada, that if you use them here, they do not work, and they will give you overly aggressive designs. So let's just talk about these correlations a little bit. One of the things to look at is, what did the axes look like? This is, if you're familiar with Paul Main, this is kind of a famous plot in that he will put a log on one axis and a log on another axis. So I would encourage you in your spare time to just put together a bunch of random points and then see what that looks like, that distribution, and then log one axis and then log the other axes, and you'll see they'll kind of start to cluster together. So it's a way to make anything kind of fit. But again, we can ask ourselves, how much variance is in this correlation I'm using? So for the glacial equestrian clay, let's say we had an N60 of tan. So if I was trying to estimate my pre-consolidation pressure, okay, well, for 10, this is varying between 2 and 12. So that's a 600% difference. So that could suggest a pre-consolidation pressure from 200 kPa to 1200 kPa. And if you use this kind of the best fit, you'd say 470. Is that range important to your project? Same with looking for CC values. Here's a ton of different correlations. For the glacial, that same glacial lacustrine clay, using the water content limits we had, this CC could range from 0.28 to 0.55. That's 100% difference. So if you had 50 millimeters of settlement, it could be 100. If you had 500 millimeters of settlement, it could be a meter. Does that matter? Is that okay? I don't know. But you have to ask yourself that. So let's say now we're going to build something bigger. We're going to build a 12.5 meter tall bridge abutment, plus a road embankment, more sensitive design. We're going to do a more detailed investigation. So CPT, you may or may not be familiar with. So this is where we take a cone and we push it into the ground at a continuous rate. So CPT is kind of three pieces. It's this cone, which has a load cell and is measuring the resistance as it's being pushed into the ground. And as we're pushing it into the ground, there's a cavity that's expanding around the probe. And then we're measuring the friction on this piece. So there's a sleeve behind the cone, and we're measuring just that friction. And then we can also measure pore pressure. And we can stop the penetration and allow pore pressures to dissipate, and we can use that to estimate where the water table is. There's a large database of testing available that provides useful correlations. So the Greg's CPT guide or the Contech application guides are good tools. Federal Highways Geotechnical Circular 5 is also a good one. Cone tends to be more reliable and repeatable compared to other methods. Results we can use directly in design. So there's the LCPC method for piles. There's some other methods for directly predicting bearing capacity, settlement. And you can add on a lot of different modules. So you could have a GS-CPTU, which would be a gamma seismic CPT with a piezo cone with pore pressure measurement. So you can bolt on a lot of additional modules. That sounds great. You know, why don't we use CPT on every project? Well, it can be more expensive than standard methods. It doesn't return a continuous or a soil sample at all. You can use a piston sampler or push shelvy tubes, but it's less cost effective. Like you have to trip out and it's relatively slow. It's slower than it is collecting at drilling. And then it can be difficult to interpret some materials. You know, there's limitations to the correlation database. Some soils have better coverage than others. You know, it's sensitive to thin layers, which is good and bad. So as we're pushing this cone through the ground, what it's doing is you just think of your bearing capacity. You've got this stress bulb that's coming out in front. So the cone is seeing in front of it. So it's the response that you get here is the response due to the layer that it's going through right at the tip. It's also the layers that it's going through along the whole cone, as well as the layers that it's seeing in front. So it's giving you this average behavior over, you know, a few centimeters. So if you got layers that are smaller than that, you're averaging them together. And what you'll see is the cone plot will just be moving back and forth in very layered material. So, you know, it has its benefits because it's telling you you've got this system, but it also means that the correlations may not work as well. And it's important to remember, one of the key things it gives you is this thing called SBT, soil behavior type. And the B is really important. So cone is correlated to behavior. The material behaves like a clay or like a sand, which is different than the material is a clay or a sand. So an example is desiccated clays tend to appear as sands, And that's why it's best used in conjunction with traditional methods, so we get the best of both worlds. So if we go back to this site, what I've done is I've added these interpretations. So these are the same interpretations we have made before using our correlations. And now I've added the cone data shown in blue. And ideally, as we add more testing, we're looking for our results to come together. That gives us more confidence in our interpretation. So we'll look at some, and I'm going to go through some more tests here to kind of look at why some may or may not agree. And on here, we've got some relatively good agreement, but then we've got these areas here where we're just seeing a large disagreement, and that could be significant for a project. And we need to be thinking, okay, in context, what do these results mean? Does it matter? So if I'm thinking about this abutment, I've got a 12.5 meter high embankment, it's roughly 250 kPa load. What does this mean for my interpretation? So what I've added here is this orange line is the effective stress. Gray line is the load. So that's the effective stress plus the load. What this is saying is that the glacial clustering unit will become normally consolidated when I build this embankment, which means I should have more pore pressure generation, more settlement. I need to be careful about my assumed strengths. So this is probably a good time to introduce some more advanced lab testing. Some of the more common ones are Traxio. Can conduct those following different loading, consolidation, drainage conditions. Generally, we use a constant cell pressure. So that's the all-around pressure. And the sample is sheared. We use it to assess drained, frictional, and undrained strengths. And we get this kind of angled failure plane. There's also DSS. May be less familiar with this. This is the whole sample sheared at a constant volume. And it's useful assessing shear strength versus shear strain. It's useful in liquefied shear strengths. So this is where we have the sample. It starts off as in a ring, and then we're shearing. So you can see this angle developing here. So we apply a shear stress, and we're looking at this angle. So that's our shear strain. So we can relate those together. And then there's direct shear. So we consolidate the sample under constant stress, and we do drain shearing along a very thin horizontal plane. And it's useful to assess the drain peak and residual strengths and how many millimeters to failure. So we might use, if we're building TARPs or trigger and alarm response procedures, we might use DSS in thick clay layers to figure out, okay, how much strain am I going to allow for my instrument, for my monitoring? And you might use direct shear if you had a thin weak layer or a slick-sided layer, and you're saying, I want to limit my deflection so I can still be inside my peak strengths. And just to kind of drive home Traxial tests, when we do Traxial, like a CU test, or a drain test, the tests themselves, they start at the same stress here in this example, and they finish on the same failure surface. But our undrained strengths are much lower in this case if we have a normally consolidated or lightly over consolidated material. And this is due to pore pressure generation. So when we look at this, I can get my frictional envelope, and I can estimate what my undrained shear strengths are from the same test, but they're much different strengths. So my drain strength might be much higher than my undrained strength. So if I come back and I'm looking at my undrained strengths, what we've done is we've got an estimate of undrained strengths from the SPT. We've got an estimate from CPT, and then we've done Traxial in the purple triangles, and we've done DSS. So we've taken Shelby's from 4.5 meter depth, So that's this kind of layer here. And we've run both these Traxel DSS, and we've taken them at the effective stress. So that would be those tests. The expected load, so that's way down here, and then halfway in between. From the CPT, pre-consolidation pressure is about 100 kPa. So that means these stress increments down here are normally consolidated. So then it comes to design, and I have to ask, okay, well, is my strength decreasing? Which strength should I use? So the first question, again, we're showing undrained strength ratio. So this is my undrained strength divided by the vertical effective stress. So is my strength decreasing? No, but my strength ratio is. There's a good paper by Charles Ladd describes using this stability of stage construction is the paper, and it introduces a Shan set model. And it's useful in understanding what we're talking about here. So what he's saying is the undrained strength ratio is the normally consolidated undrained strength ratio, and then it's related to that based on how over consolidated you are. So if we look at 4.5 meters depth, water table at 2 meters, effective stress is about 65 kPa. If we look at the figure, this kind of works out to about 30 kPa. Like if we put it through here, so we've got over consolidation 100 divided by 65. It tells us undrained strength about 30. At 315 kPa, so way down here, if we take this and convert it to undrained strength, it's about 66 kPa, but our ratio is 0.21. So our ratio is decreasing. Here we're at like 0.3 something, down here 0.21. But our strengths are increasing because we're at a much higher effective stress. So just kind of go through that again. Right now, our undrained strength is 30 kPa. So this accounts for the pore pressures that develop as loading and shearing occur. When the effective stress increases due to the embankment load, undrained strength will increase to 66 kPa. However, to get this, we need the foundation to consolidate. So we need to dissipate the excess pore pressure so that the effective stresses increase. So why this is useful is our in-situ testing, it's only just getting to where this material is normally consolidated. That pre-consolidation pressure is around 100 kPa. So if I'm just getting my undrained strength ratio or making the assumption based on the in-situ testing that I have, it's all over consolidated. So I'm overestimating what this strength ratio is. If I'm taking that, I'm trying to project it forward, then maybe I have the wrong undrained strength. Okay, so question 2. We'll notice here our Traxel results are a lot higher than our DSS, and they're more than 100% higher. So why are they higher? Should we use our Traxel or DSS? And this is due to the mode of failure and the shape of the failure surface. So what's important to remember is Traxel compression strength is about 40% higher than DSS, which in itself is about 30% higher than Traxel extension. In embankments and foundation bearing capacity, we tend to use DSS strength, which is the average strength along this failure surface. So what we have here is an embankment, and you can say that this upper bit is in compression, a lower bit is in direct simple shear, and this is in extension. And it works out that if you average along this failure surface, it's around the DSS. You'll notice if you use correlations from Stark, you're looking at first-time slides. For slopes, slope failures are typically to the toe, and they start at the crest. Well, that's just Traxel compression. So you'll see, like in slopes, we might use a different strength than we would for embankments. So it could be the exact same site, and you might use different strengths for different applications. But wait, the triaxial strength here is more than 40% larger than our DSS strength. Why is that? Well, this is again where we have to have everything in context. So the sample here is bars, it's layered. So here's an example, and the triaxial failure is going across the layers. It's giving it extra strength. We have these interbedded layers of sands and silts that are giving it more strength. The DSS failure itself is along these layers. So we're not seeing that increase in strength. So we need to be mindful of those conditions when we're selecting the tests and when we're interpreting the results. So running towards our conclusion here, so lab tests, there's a lot of benefit. We just saw that. We can test a wide range of stresses. We can test well beyond what the in-situ stress is to see how our soil will behave under the loads we're expecting during design. We can improve our understanding of the soil behavior, and we get results, real results, instead of relying on correlations, which help confirm our assumptions. We'll use the correlations, then we'll do the testing. Okay, do these make sense? And we typically require some parameters from these tests for advanced numerical models. However, tests can take a long time to finish. They can be expensive. The results can be confusing. And we have effects of sample disturbance, pore fluid issues, non-representative samples. Some materials are really difficult to get undisturbed samples out of. Sands, gravels, soft clays, stiff clays. Sometimes the samples that you can return are the best of that ground material. And if you build something, it will find the worst. Samples generally need to be saturated, and that may not match the in-situ conditions. And we always have to ask ourselves, why does my data match or not match? And some correlations are better than others, and there's considerable scatter in the correlations. So like I said, be aware of these log-log plots. And the soil database used in the correlation may or may not be applicable to your site. And then some correlations are for the same parameter, but they're a completely different strain or strength levels to your application. And this is an example I pulled from a job that I was on. And here, what we're showing is this is the pre-consolidation pressure. And again, I'm showing the in-situ effective stress. And this is the expected stress after the embankment is built. The blue line here is the pre-consolidation pressure interpreted from the cone. And this guy here is the interpreted pre-consolidation pressure from the odometer. So the lab test gives significantly different results than the in-situ test. Based on the expected stress levels, the design would be hugely different. So this is about, on this project, this would be about a $20 million difference in design. So you have to ask yourself, which one do you believe? And in closing, lab and in-situ testing, they're part of a larger process. You need to understand how the data is going to be used to properly scope the testing. And I encourage people to start simple. Same with modeling. Start simple. We can gain a lot of information from simple tests using simple models, simple labs, simple in-situ investigation. It helps us access the experience of others. Those tests are more common. You're going to get more correlations. So you start there and you start building. And more expensive testing does not always mean better. The more sophisticated the testing is, we need to have a better idea of what we're doing and why we're doing it. And they may not always give us a useful result. So when we're scoping and interpreting the test results, it's important to recognize testing builds on each other. So we use those simple tests to understand more complicated results. And using multiple methods is recommended as confidence increases, data from different sources comes together. And when it doesn't come together, then we can ask some informed questions. So thank you for your time.